Welcome all. In this lecture, I will show you that is how to find the left cossets. The concept of the left cossets were discussed in the earlier lecture. So in this lecture, I will show you that is how to find the left cossets, and there will be another discussion, that is the discussion about classes. Now suppose there is a question, that is find the left cossets of the proper subgroup capital H of the group capital G. Now the group capital G concerned about the multiplication table 28.8 discussed before in some of our lectures, but I will show you again that particular table. So this is the particular multiplication table. Actually this multiplication table is the common table for so many groups which are isomorphic one. For example, this group elements may be the symmetry elements for the equilateral triangle, and this particular group may also represent the permutation group which was discussed in some earlier lecture, and this particular group also represent some matrices, some particular matrices which were also discussed in our earlier lecture. So whatever it is, but this particular elements form a group, and this is the particular multiplication table for that group G. So we have discussed that is how to construct the multiplication table. I will refer you to go through the lecture about the multiplication table again, so that you can clearly understand this particular table. So this is the multiplication table for the particular group G which we have discussed. Now our task is that for the particular group capital G, there is a particular proper subgroup capital H, and this particular subgroup consists of the set of elements capital H is equal to IAB. We have also discussed the concept of subgroup. So IAB, these three elements is a subgroup corresponding to the group capital G. In capital G there are total 6 elements, and in the subgroup there are 3 elements IAB, and we are writing this proper subgroup as capital H. So capital H consists of 3 elements I, A and B. Now what we have to do, that is we have to find the cossets corresponding to the subgroup capital H. Now capital H itself provides the first left cosset. Formally the cosset is I into H. So to find the first left cosset, what we generally do is to multiply the identity element I with the subgroup capital H. So we have multiplied it, I into capital H, so that is equal to I into I, comma I into A, comma I into B. So this will give you I into I is I, and I into A is A, and I into B is B. So IAB, that is the subgroup itself, is the first left cosset corresponding to capital H. Now we choose an element not already selected, that is C. C has not been selected, and what we can do, we can multiply C with respect to capital H. So this is CH. So what will be the CH? CH is equal to C into I, comma C into A, comma C into B. Now C into I is C, that is quite obvious, but what is CA and CB, that we can find from the multiplication table, and we know that is how to find the products. For example, suppose C into A, C into A will be D. Similarly C into B, that will be E. In this way we know that is we have to find the products. So after finding the products, we can show that CA is equal to D and CB is equal to E. So there are total 3 elements for the coset CH, CD, E. Now if you observe the set of elements contained in these two sets, then these total 6 elements cover all the 6 elements for the group capital G. So we write in this way, that is, these two cosets of capital H exhaust G. This is in mathematical language we say that as these two cosets, they cover all the 6 elements of capital G. That is why we say in this way, that is, these two cosets of capital H exhaust G and are therefore the only cosets. So no more cosets will be there. These two cosets are only cosets of capital H. Now how to find the index of capital H? The rule is that small g by divided by small h, where small g is the number of elements in the group G, that is 6, and what is small h? Small h is the number of elements in the capital H, that is 3. So 6 by 3 is equal to 2. So the index of capital H will be 2. Now we have already completed our task, but one thing to note is that suppose we have started by multiplying identity with the given subgroup to find the first left coset, but we can also multiply any elements from the group G. For example, we can multiply capital D also. Suppose we have selected capital D and we have multiplied capital D with H, then I, A, B are the elements of H. So DH will be DI, DA, DB, and from the multiplication table we can find all the products. So from the multiplication table as shown here, you can find all the products. So from there you just find, that is, what is DA, what is DB. So this particular coset will be D, E and C. Now choose another element which was not selected before, suppose B. Now you multiply B with H, then just by earlier procedure, similar procedure, we can also find the elements for the particular coset BH, and the elements are BIA. Now you can see, that is, the elements of for the two cosets exhaust the group capital G. So and another thing to note, that is, in this way we can also calculate the two cosets, and the elements for the two cosets, you see that is they are almost they are same, because here it is IAB and you see that is BIA, but the elements are same, and here they are CDE and here DEC, but the elements for the two cosets again same. So same two cosets would have been resulted. Now one important property, that is, if capital H is a normal subgroup of capital G, we have already defined what is a normal subgroup. So if capital H is a normal subgroup of capital G, then its left cosets themselves, if you calculate that what are the left cosets of capital H, then those left cosets will themselves form a group, that is, consisting all those left cosets, and they will also form a group. That is one property for the capital H. Now we will discuss another topic, that is about conjugates and classes. Our second example of an equivalence relation is concerned with those elements x and y of a group G that can be connected by a transformation of the form y is equal to Gi inverse x into Gi, where Gi is an appropriate element of capital G. So y is equal to Gi inverse x into Gi. This is a particular relation where Gi is an element for the group G. So this is a transformation relation. Thus x is equivalent to y if there exists an element Gi of G such that y is equal to Gi inverse x into Gi. So this is the definition for the equivalence relation. You just again look it carefully, that is, this is the particular transformation relation, and this is the definition for the equivalence relation of x and y. So if y is equal to Gi inverse x into Gi, then we can say that x is equivalent to y. Different pairs of elements x and y will in general require different group elements Gi. So, when you calculate this transformation relation for different pairs of elements x and y, in that case you will require different group elements Gi. For example, this is valid for a particular element for the group G, and the same relation for another pair of x and y, you have to use separate element from the group G, and elements connected by this relation are known as conjugate elements. So, suppose if you focus on this relation, then we can say that is x and y are conjugate elements. Now, we first need to establish that this does indeed define an equivalence relation, that is this relation, this particular relation, this relation defines the equivalence relation, that is x is equivalent to y. So, we will just discuss the properties of the equivalence relation, and we will try to understand that is it in accordance with the given relation. So, first of all, that there is reflexivity, that is x is equivalent to x. Now, this is the definition, that is y is equal to Gi inverse x into Gi. So, suppose if both are x, and if we choose the element identity from the group G, then we can write x is equal to I inverse x into I. So, this relation which has been found from this relation only, this relation establishes that x is equivalent to x, that is this relation suggests the reflexivity relation. Another relation is that symmetry, that is x is symmetric to y. Now, this is the definition, that is y is equal to Gi inverse x into Gi, and this relation implies x is equivalent to y as per our original definition that was assumed before the derivation. So, y is equal to Gi inverse x into Gi, that particular relation implies x is equivalent to y, and therefore, that is from the same relation, we can also write the relation in this way, that is x is equal to Gi inverse to the power inverse then y into Gi inverse, that is this relation and this relation is just same, just the position of x and y has been interchanged. Now, since Gi belongs to capital G, Gi is any element for the group capital G, so Gi inverse will also be an element for the capital G. Naturally, from this relation we can say that is y is equivalent to x. If this particular relation suggests that x is equivalent to y, then this particular relation will also imply that is y is equivalent to x. And there is another property, that is transitivity property. So, x equivalent to y and y equivalent to z will imply that is y is equal to Gi inverse x into Gi, and z is equal to Gj inverse y into Gj. We have written this equation as per our original definition of the equivalence relation. And now, if z is equal to this one, so what we can write? We can write this equation by some rearrangement. Suppose there is a element y here, again y is equal to Gi inverse x into Gi. So, what we will do? We will put the value of y here in this equation. So, putting the value of y in particular in this position, we can show that z is equal to Gj inverse Gi inverse x into Gi into Gj, and this particular relation can be written in this way, that is Gi Gj inverse, because Gi Gj inverse is equal to Gj inverse Gi inverse, they are the elements for the group G. So, we are writing this particular first two elements in this way, that is Gi Gj inverse x into Gi Gj. Now, since Gi and Gj belongs to capital G, so Gi into Gj, product of Gi Gj will also belong to the capital G. So, this is a particular group element, product of Gi and Gj is a particular group element, and from this relation, that is z is equal to, suppose you can take that is Gi Gj is equal to Gk. So, suppose Gi Gj is equal to Gk, so z is equal to Gk inverse x into Gk. So, this relation suggests that is x is equivalent to z. So, transitivity relation holds here. Transitivity relation means that is if x is equivalent to y and y is equivalent to z, then it follows that x is equivalent to z. And these results establish conjugacy as an equivalence relation and hence show that it divides capital G into classes as per the definition of the equivalence relation. So, two elements being in the same class if and only if they are conjugate. Two elements will be in the same class if and only if they are conjugate. So, there may be some immediate corollaries. For example, if capital Z is in the class containing capital I, then we can write that is capital Z is equal to Gi inverse I into Gi. Now, I into Gi is Gi. Now, Gi inverse Gi is equal to I. Thus, since any conjugate of I can be shown to be I, because we have initially assumed that is Z is an element which is in a class that contains capital I. But here we have shown that is Z is equal to I. That means that since any conjugate of I can be shown to be I. So, conjugate of I is capital I only, and the identity must be in a class by itself. So, in the class containing the identity, there will be only that particular identity element, and identity element must be in a class by itself, and conjugate of the identity element is the identity element itself. Now, if x is in a class by itself, suppose x is an element that is a class by itself like the identity element. Now, suppose we are writing the definition of the equivalence relation, that is y is equal to Gi inverse x into Gi, but it must imply y is equal to x because we are assuming that is x is a class by itself. Now, this relation must imply that is y must be x. Now, we can write any element x in this way, x is equal to Gi inverse. Now, you see that is Gi inverse is equivalent to identity, and identity x into I, that means x can be written in this way, and this is for any element Gi. And so, what we are doing now, that is as y is equal to this one, that is as per the definition of the equivalence relation. So, this particular equation can be written in this way, where what we are doing, we just putting a bracket here in this position, Gi inverse x into Gi, but Gi inverse x into Gi, that is I. So, x is equal to Gi y into Gi inverse is equal to Gi x into Gi inverse, because y is equal to x. So, x is equal to Gi x into Gi inverse. So, this relation suggests that is x into Gi is equal to Gi into x, because if you multiply Gi inverse from the right, then you can show that x into Gi is equal to Gi into x from this relation. But this relation is actually the commutation relation. Thus, commutation with all elements of the group is a necessary condition for any particular group element to be in a class by itself, because we have assumed that is x forms a class with itself. So, if it is true, then this commutation relation must hold. In an abelian group, each element is in a class by itself, because the elements of the abelian group commutes with each other. So, we can say that in an abelian group, each element is in a class by itself. Now, in any group capital G, the set S of elements in classes by themselves. Suppose there is a particular group capital G, and for this particular group capital G, there are some elements which forms the classes with themselves. For example, and just before we have discussed the case of identity element. Identity element forms a class with itself. Similarly, we have also assumed that suppose x is an element which forms a class with itself. So, there may be similar type of elements which forms a class with itself. So, if you consider all these elements, so that they will form a set of elements S, and the set of elements S, the set S of elements in classes by themselves is an abelian subgroup. So, if you just consider all those elements contained in the set S, that will be a abelian subgroup of capital G. We have already shown that I belongs to S, I is a element of that particular set S. And so if further suppose we are assuming that x and y are another two elements which are classes by themselves. So as per the definition of the classes, x into gi will be gi into x and y into gi is equal to gi into y, because we know that the elements which are classes by themselves and they commute through the elements of the gi. So x into gi is equal to gix and y into gi is equal to giy for all gi belonging to G. Now you just focus on this particular relation. Suppose we are writing xy into gi is equal to y into gi is equal to giy from this relation. So we are writing y into gi as gi into y. Now x into gi, first two elements, we are writing x into gi as gi into x. So xy gi is equal to gi into xy. Now what is xy? Xy is a product of the two elements xy, x and y. So that particular element will also be in the group G or the set S. So xy is an element that is contained in the set S. That is, it actually proves the closure property for the set S, because it is also one type of commutation relation as described here. Just we have used the product of xy here. So you can name the product as z. Suppose xy into x into y is z. So z into gi is equal to gi into z, as this relation holds. X into gi is equal to gix, y into gi is equal to giy. Similarly, z into gi is equal to gi into z. So z is also element for the set S and it establishes the closure property for the set of elements S. Now another thing is that suppose x into gi is equal to gi into x. So this implies x inverse into gi is equal to gi into x inverse. That is, we prove this relation from this relation. Now the inverse of x belongs to S, as this relation suggests. You just assume that is inverse of x is another element. Suppose it is r, so r into gi is equal to gi into r. So r is also contained in the element in the set of elements S. So inverse exists. That means the set of elements S form a group, and this group is abelian group because commutation relations hold. That is why this particular group is abelian group. Now just in the beginning of the lecture we have shown that is how to find the cosets. So now from the same multiplication table I will show you that is how to find the classes for a particular group. Suppose we are considering the same group G that we have shown here. This is the same group G, and for this particular group G we will find the classes. So how to find the classes? Now the element I is in a class by itself. We have already discussed that. That is, the identity element is in a class by itself, and we need consider it no further. That is, we are not considering it further. Now consider next the results of forming x inverse A into x, where the x runs through the elements of G. Suppose we are considering the product x inverse A into x, because we have already defined that is what do you mean by classes, and in the classes conjugacy relation holds, and from the conjugacy relation we will show that is what are the elements for the classes. So at first we are considering this conjugacy relation x inverse A into x, and we will find that is what is the result for the x inverse A into x, where x is any particular element for the group G. So there are 6 elements in the group G, I, A, B, C, D, E, but we have already considered I. Next we will consider another elements of the group G. Now we have written the conjugacy relation x inverse A into x. So x is an element, any element for the G. So what is the result for x inverse A into x? So what we have shown, that is we have step by step just written different values of x. For example, first element is the identity element, so I inverse A into I. Second element is A, so A inverse A into A. Third element is B, so B inverse A into B, and in each case we are finding that is what is the result for the conjugacy relation. and to find out the result, what we need this particular multiplication table, and there are in some position there is I. So you have to note down this particular position. Why? Because you see that is A into B is equal to I. It means AB is equal to I. That means B is equal to A inverse. Similarly, you see that is here is also I. That is BA is equal to also I. Now you see this I. There is a position I here. So C into C is I. So we have to find that is where there is I, because from this element, identity element, you can find the inverses. So that values you have to use to find out the resultant product of the conjugate relation, that is x inverse A into x. So we have used those particular relation from this multiplication table, and ultimately we have shown that is if you calculate the value for this particular conjugation relation, so only A and B are generated. You see there is no other elements apart from A and B. So from this particular conjugation relation, only A and B are generated. So it is clear that AB is one of the conjugacy classes of G. So AB, these two elements form a class, and we can use this conjugation relation, that is x inverse A into x, that is equal to B. Similarly, we can also check, that is if you use x inverse B into x, as we have started from x inverse A into x, so instead we can also use that is x inverse B into x, and by the same method we can also show that in each case either A or B is generated. So it means that A and B are conjugate elements and they form a particular class. So A and B, these two elements form a class. Now you take another conjugation relation, that is x inverse C into x, and just as we have proceeded before in the similar method, we have to put the values of x step by step, that is starting from I to E, and from this particular conjugation relation and with the help of the multiplication table, we can show that the product of x inverse C into x are C, E, D, C, E, D. So ultimately what elements we have obtained, that is 3 elements we have obtained. If you check E is repeated, C is also repeated, D is also repeated. So ultimately total 3 elements have been generated, that is C, D and E. So these 3 elements also form a class. So ultimately 3 conjugacy classes are there. One is the identity element. So identity element itself form a class. Then there is another class where there is A and B, and there is another class where there is C, D and E. So total 3 classes are there in this particular group G, and with this example I have shown you that is how to find the classes for a particular group G, and I hope you have understood this lecture. And if you have any doubts, then I suggest you to read the book of Mathematical Methods for Physics and Engineering by Riley, Hobson and Benz, and I also thank you for listening the lecture.